So the ratio test, what we're going to take is an infinite series, and we're going to try to use the ratio test to establish whether it converges or diverges. So what you do, the first thing you do is you form this ratio. All right? So a sub k just means some term. What does a sub k plus 1 mean to you? It means the next term, right? So you're basically what you're doing is you're doing a ratio of the next term to the previous term. So one thing that would happen on this is, I want you to think about this a little bit, because you're going to find that a lot of these tests, the convergence has a lot to do with 0 and 1. Those are kind of big numbers on this. So if you took a series, for instance, that we know converges, okay, here's an example of something that we know converges. You could do something like 1 over k to the second, k equals 1 to infinity. You guys know what kind of series that is. You want to start getting these things down, and it'll take you a few weeks to get that. What kind of series is 1 over k to the second? It's called a p-series, okay? That's a p-series, and we know that a p-series converges when what happens? What does that exponent have to be? Bigger than 1, okay? So if it's bigger than 1, we know we converge. If you wrote out the terms of the p-series, the first term would be 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so forth. So you'd have 1 plus a fourth. It's real easy to write these things out once you see the pattern. So that would just be 1 over a perfect square, right? Okay? Well, here's kind of what the ratio test is really saying. It's saying if you take a term, any term, preferably way, way out there, and if you did the ratio of 1/9 to the previous term, that would be 1 over 9 times 4/9. So that would be 4 over 81. So you're going to establish that in general, that ratio is between 0 and 1. That would be a condition for that to converge. And if you went further and further and further out in that particular 81, why did I get 81?
You wrote 4/9.
Okay, let's try this. Same result though. Okay, so that should be 4/9. My point is, isn't 4/9 between 0 and 1? Okay, now that doesn't prove anything. That just shows you for that particular term, that condition holds. But if the terms are decreasing, wouldn't that always hold, no matter where you are? Okay, because what you're doing is you have positive terms. So if you can show generally that this ratio of a sub k plus 1 to a sub k plus 1 is between 0 and 1, then you're going to converge. If you're bigger than 1, then what's happening is going to be that the ratio of those terms are getting larger, so it's going to have to diverge. And if r is equal to 1, then you're going to be inconclusive. Okay? So does that make some sense? Okay? See, if you went through and did this, another way to look at this, if you did the next term, like if you did the ratio of 1/16 to 16 over 9, if you ended up doing that, you would just have 9 over 16, and so forth. So that value is always going to be between 0 and 1. That's why it converges. Okay? So here's what we're going to do. So on the ratio test, first thing you want to do is we're going to let r be this limit. Okay, so we're going to do the limit as k goes to infinity, and we're going to do a ratio of two things. We're going to do a sub k, which just goes in the denominator. Now, what goes in the numerator? That would be the next term. So what would k become in the next term? It's not k anymore. What is it? It's k plus 1. So that would be 1 over k plus 1 factorial, like that. So when you do the ratio test, you're always doing that. Whatever the series that expression is goes there, and then the next term goes there. Just change all the k's to k plus 1. All right? So it's real simple to start. Okay? If we do this then, now you can do this in your head. What you're doing, I'm going to write the step a couple of times, and I'll kind of start omitting this. What you're really doing is you're doing 1 over k plus 1 factorial, and you're dividing by that. So if you divide by 1 over k factorial, what are you really doing? You're multiplying by the reciprocal, right? So that's going to be times k factorial over 1 like that. Now, you guys can jump immediately to that step if you want to. You need to realize that you're doing this ratio, so really you're multiplying by the reciprocal anyway. So that's going to leave us with the limit as k goes to infinity, k factorial over k plus 1 factorial. Now, what do we want to happen on that limit in order for it to converge? What's it got to range from? Where to where? 0 to 1, okay? So if that turns out to be between 0 and 1, including 0 but not including 1, that's going to converge, okay? If it's greater than 1, it's going to diverge. If it's equal to 1, it's inconclusive. So the ratio test is not always conclusive, okay? So what we want to do on this then is we want to write these things out. So you're going to work a lot with factorials when you do this. So what we're going to do is going to write this out, okay? This is the key. So if you do a factorial, what do you do? Like if you're doing 4 factorial, what do you do? You write down the first term. Then what do you do? Then you go 1 less until you get to 0, correct? So what you do when you do k factorial is how do you write that? You write the first term's k. What's the next term?
K minus 1.
Good, k minus 1. And then it would be k minus 2. Now you don't know what k is, so it would just take that pattern forever, right?
So it would just be k minus n minus 1.
Right, okay, then eventually you would get to 1, right? So it's the same idea. You're just writing kind of a general formula for that like that, okay? Now watch the next one carefully, okay? So if you did k plus 1 factorial, well, what do? You always write the first term down, right? So what you would have is you would have k plus 1, that's the first factor, correct? Now what's the next factor? It's really k plus 1 minus 1, right? Okay, which is what? K. And then what's the next term?
You're canceling everything on top.
Yeah, it's just going to be k plus 1 minus 2, and so forth. Now, you don't have to write it out that way. I'm writing it out specifically that way so you can see what I'm doing. What you want to do, sometimes students don't catch on to this immediately, so what you're really doing is you're doing this. Okay, when that goes down 1, doesn't that just go to k? And then when k goes down 1, that's k minus 1. Then k minus 2, and so forth, and eventually you'll hit 1. Okay, so tell me if that makes sense. Okay, now, what do you notice?
1 over k plus 1.
Yeah, you got a lot of things canceling, don't you? Good, so let's see, that will cancel. Everything, in fact, will cancel, except you'll be left with, and I think you said 1 over k plus 1, right? Everybody with me on that? Okay, so what you end up with is you end up with the limit, k goes to infinity, of 1 over k plus 1. Okay, like that. Now, what is the value of that limit? That goes to 0, doesn't it? Okay, because what you really have is you really have 1 over infinity, and 1 over infinity goes to 0. Okay? So, would that converge or not converge based on the ratio test? Is it okay for that to be equal to 0? Yes, it says right there. Always look back at these things. When you're doing your homework, look at this thing. What I'm trying to do as I'm teaching this is go back to the definition. That's what you always have to do, and that will tell you how to apply the ratio test. So what you would say therefore, and you can use the little 3 dots if you want to. That's a good shortcut to just say therefore, the series 1 over k factorial converges, and then you need to state what test you use. So you say converges by the ratio test. That's the way I always want to write your conclusion. Like if you were doing a test, on a test, you would need to write, therefore it converges by the ratio test, and then your work up here would be showing that you're using the ratio test. So when I grade your 3rd exam, I have to check everything. I have to go through and check that you are indeed using the ratio test, because sometimes students just write a bunch of stuff on their paper, and then they say, oh, it converges, okay, like magic, okay, so we don't want to do that. We want to do it correctly. So it's kind of like you're not really doing a proof, but you're demonstrating your knowledge of proving by the ratio test that this thing converges. Okay, does that make sense to everybody? Okay, yes or no? Okay, all right, ratio test is not too bad. The key thing is the algebra and then getting down to some limit that you can evaluate, okay? All right, so let's go to the next thing here. Now, one thing that I didn't kind of failed to mention on this is on the ratio test, all the terms got to be positive. That's one thing that you got to verify. If they're not positive, can't use it. Okay, so if you were dealing with a alternating series where you had some negative terms in it with oscillating terms, you couldn't use the ratio test on it. There's something else you have to use. Okay, so this particular problem, let's just write out a couple of terms in the sequence. So this one's kind of weird, and I think this is a mistake. That was supposed to be k equals 1. Do you know why?
If it was 0, it would be...
Well, then you'd have 0 to the 0, which is kind of an undetermined thing, right? Okay, that was a typo, my fault. Okay, so what you'd have here is your first term would be 1 to the 1 over 2 to the 1. Then your second term would be 2 to the second over 2 to the second. It'd be the same thing. Okay, then it would be 3 to the third over 2 to the third. Then 4 to the fourth over 2 to the fourth, like that, and so forth. Okay, so that's the pattern. The numerator is just k to the k. So eventually you'd have like 10 to the 10th, right? The denominator is 2 to a power. Okay, so are all the terms positive? That's key. Without a doubt. Okay, just write a few terms out. Once you see the pattern, that thing's never going to change to a negative number, so that means the ratio test is applicable. Okay? All right, so here's what we do. We go ahead and write our ratio. So what we're going to do is a limit as k goes to infinity. All right, now what we're going to do is this. When we do this ratio, I'm going to do it one more time like this. Tell me what goes in the denominator on this. Same thing, whatever I gave you, right? So that's just the generic formula k to the k over 2 to the k. So that's what goes there. Okay, what goes in the numerator? What do? You change all the k's to what? K plus 1. Okay, right? So we want to do that. So we're going to have k plus 1 to the k plus 1 power. I'm going to put that in parentheses also. Then we'd have 2 to the k plus 1. So you're going to get into lots of expressions that are kind of messy. And you got to work out some algebraic simplification on this then. Okay? All right. Well, the next step you can kind of do in your head. And I don't mind if you bypass that first step. I'm going to start bypassing that. You just need to know that that's the ratio you're doing. So what you're going to do is you're going to write this as k plus 1 to the k plus 1 power all over 2 to the k plus 1. And then you're going to multiply by the reciprocal, right? Because since you're dividing by a fraction, you're going to multiply by the reciprocal. So you'll have 2 to the k over k to the k like that. Okay, so far so good. Terms are positive. Ratio test is set up. Now what we got to do is we got to do some algebra. And typically, some things are going to cancel out. So one of the things that you're going to do with this algebraically is, like if you have 2 to the k plus 1, how can you split that up? 2 to the k times 2 to the first, correct? Because after all, when you multiply, you add the exponents, right? How about this k plus 1 to the k plus 1? How do you break that up? Same idea. You'd say k plus 1 to the k times k plus 1 to the first. Okay, so you're going to break that up, yes.
Oh, never mind. I was about to say, could you break up the parentheses?
Yeah, okay. You can also subtract exponents. I like to just kind of write things out on this. So I'm going to go ahead and write this out. So we've got the limit. K goes to infinity. And then I'm going to write the k plus 1 to the k plus 1 is k plus 1 to the k times k plus 1 to the first times 2 to the k. So that's what you have in the numerator. Then the denominator, write the 2 as 2 to the k times 2 to the first, and then times k to the k like that then. And then we'll have some things that are going to cancel out, and then we'll kind of see where we're at. So what cancels?
2 to the k.
Okay, so that gets rid of that. That helps a little bit. What could you do with this 2?
Pull it out.
You can pull it out if you wanted to. Okay, that's what I'm kind of used to doing. So I'm going to pull that out of the limit. So we'd have 1/2. And then we'll have the limit as k goes to infinity. Let's write what we have left. It looks like we have k plus 1 to the k times k plus 1, then all over k to the k like that. Okay, then that's what we're going to end up having. So what we want to do from here is you want to kind of think about whether this what happens to this this limit then. Okay, there's several ways you can look at this too. Okay, one way you can look at this is if you look at this term right here. This is a way to do this in your head. Okay, when you're at infinity, does that 1 really make much difference?
No.
Very little. So if you just ignore that 1, then you can think of those things canceling. So if you get way, way far out in that limit, those things are roughly the same. Everybody agree? Mm-hmm. Okay, real close. So you end up with that. Now what would be the limit of k plus 1 if k goes to infinity? That'd be infinity, wouldn't it? Okay, so you would end up having what kind of result? Converge or diverge? That's going to go to infinity. That whole limit's going to go to infinity. So what you can do, if you want to, you can reason it out that way and just realize that those things, for all practical purposes, cancel out. Now, I'll tell you what I did on this. Now, you can do that in your head if you want to. But what I did on this is you can also write this like this. These two things right here could be put together in the same, under the same exponent. So you could write this as k plus 1 over k to the k power times k plus 1 like that. Okay, and then this thing right here, I'm going to write one more step. This is a more analytic way to look at this other than just doing it in your head. Okay, you could write this, see on this, you could split this up. If you have k plus 1 over k, you could write that as k over k plus 1 over k, which is 1 plus 1 over k to the k power times k plus 1. Okay, so this is a more analytic way to look at this. Now, if you look at this, where would this thing right here go if it was infinity?
0.
That'd go to 0, right? So what you would really have is you would have 1/2, and then you would have 1 plus 0 to the k times k plus 1. Okay, like that. Now again, you don't have to do this necessarily. This one's easy enough to reason in your head. But what you would have is you'd have 1/2, 1 to the k, k plus 1. What is 1 to any power? 1. Okay, so what you would have is now you would end up with the limit. I've already done the limit because that's going to infinity. So you would have 1/2 infinity plus 1. Like I told you, it goes to infinity. You don't have to necessarily go through that because it is kind of good to be able to see that although they don't really cancel when you're going to infinity, for all practical purposes, they're roughly the same, right? So then you can reason it out that way if you want to. Save that. Okay, does that make sense what I did then? So what you would say then on this one is you would say, therefore, and you can just write the series a sub k. You don't have to write k to the k over to the k. You're going to say diverges by the ratio test. So that's two pretty good examples of ratio tests. It's not that hard to do, but you do have to algebraically manipulate these expressions to figure out what happens when you take that limit. That's the most challenging part of the problem, is the algebraic manipulation, in my opinion. Okay? All right, so do you guys follow what I did okay with that? Okay, so we would know that, and you know, if you look at this part B, if you look at this, it's not clear necessarily that it diverges, but what's going to happen on this, what's going to happen, I think, with this one is this numerator outpaces the denominator. If you look at that, that's why that thing diverges. You can tell on this one by writing some terms out that it's going to diverge. And that's a reasonable way to start these problems out, is write terms out to get a sense of whether it might diverge or converge. Sometimes you can tell, sometimes you can't. Yes?
If on the test
we come across a problem like this and it allows us to very easily see that it diverges, would you accept
Yes.
that? Okay.
Yeah, I'm talking about like this step
Yeah.
right here. Like if you went ahead and just said, okay, that goes to infinity, that's fine, because I want you to be able to see things like that, reasoning out. This is a more technical way to show that, but you would be okay if you did that like that, okay? Like on this part A, you want to go ahead and do all the simplification and get that on your paper, then it's clear when you do that. So once you get that to something that you can do in your head, then you can do it, okay? Okay, all right, let's go ahead and do our break. All right, so let's say I'm going to do one more ratio test example. And then we're going to look at some different types of tests. So one of the things I'd recommend as you're going through this section is, maybe make some flashcards out or something on these different tests. I mean, you could cut out or make copies and cut out these boxes where I have everything in there. So you want to kind of start getting these in mind. The ratio test, again, we always want to make sure we have all positive terms. So pretty much you always just do that in your head. I'm going to go ahead and write some terms out on this then. So if we let k be 1, we'd have 1 to the 6th over 1 factorial, then 2 to the 6th over 2 factorial, and then 3 to the 6th over 3 factorial, and so forth. So the key is we do have positive terms. So we know that the ratio test is applicable to this situation, okay? All right, so let's go ahead and get this one set up. Now this time what I'm going to do is, instead of writing that first step, I'm just going to bypass that. So what we do is you're dividing by that term. Okay, so if you just go through and take the next term is going to be k plus 1 to the 6th over k plus 1 factorial. Now instead of dividing by that term right there, what you can do in your head is just realize that you're going to be multiplying by the reciprocal of that previous term anyway. So if you want to start the ratio test off that way, you can, okay? Now what we need to do on this is we need to just kind of see what we can do with writing the terms out and see what we have here. So, all right, let's go ahead and just sort of write this stuff out. So it looks like we're going to have the limit k goes to infinity. Let's just write the k plus 1 to the 6th out. Okay, then you want to write your factorials out the correct way. So how do you write k factorial out? How do you start? You write k, then what? K minus 1, k minus 2, just to kind of get the pattern. Eventually you'll make it to 1, okay? And how do you write k plus 1 factorial out? How does that go?
K plus 1.
You start with k plus 1, then what?
K.
And just go down. So you're going to go to where? K minus 1, k minus 2. Everybody got that?
So whenever you see a k factorial on the bottom, you can just put a k plus 1 for your next limit.
What's that?
Well, I mean, we did this thing previously and before, and we figured out that the top just goes to 1 and then the bottom goes to k plus 1.
Right. You can also do this like this, which I'm going to kind of start doing. Yeah, you can write it out this way if you want to. You could also write this out as k plus 1 to the 6th. Then you could just write that, not even do anything with the k factorial. Now tell me if this makes sense. If you did k plus 1 factorial, you would write down k plus 1, then what would come next? K minus 1, so couldn't you just write that down? Is that what you're thinking?
Yep.
Good observation. You can write it that way. You either write it out, whatever you need to do as a student. This is the way I do it, is just k plus 1 factorial is going to be this, okay? Same thing's going to happen. That's going to cancel, but if you went through and did it this way, everything's going to cancel anyway. Now, you still have that leftover k to the 6th there too, don't you? Okay? All right, so then what you would have is you'd have the limit as k goes to infinity. Okay, what would happen to this little piece right there that I circled? What would that go to? K plus 1 to the 5th, right? Okay, because you could subtract those exponents, or one of them would cancel out, so you would have k plus 1 to the 5th, and then you would have k to the 6th like that then, okay? Now again, this is something that you could figure out in your head. There's more than one way to do this, but if you look at this, just think about which is bigger ultimately. Is the denominator bigger or is the numerator bigger?
Denominator.
Yeah, so see, for all practical purposes, when you go to infinity, does that 1 really make any difference? No, so you could think of this as k to the 5th over k to the 6th, correct? Okay, and then that would be 1 over k, all right? And then if k goes to infinity, you're going to have 1 over infinity, so that's going to go to 0, okay? So that would be the value of that. And again, if the value of this ratio is 0, what do you conclude? We converge, okay? So we would just say then, therefore, we'd say the series, you can just say the series, or you can just say series way of k, you can write it that way if you want to, converges by the ratio test. Okay, so that's how you do that. So you're always looking at the convergence of that ratio of the next term to the previous term. Okay, so nice, not that hard of a test to do. The only thing you get into sometimes is some algebra that's a little tricky. So you can write this out this way if you want to, or you can write this out like this, okay, either way. So one thing that you want to get in mind is, let's say for instance you had k plus 2 factorial, okay? Well, what do? You write down k plus 2, right? Then what's next? What's lower? What's the next lower term?
K plus 1.
K plus 1, then what? K. But then it would be k factorial from then on out, wouldn't it? Because then it would be k minus 1 like that. You could even write this way. You could write it as k plus 2, and you could write it as k plus 1 factorial. Make sure you get that in your mind, how to write those factorials out. Okay, does that make sense to everybody? Okay. Right, whenever you have factorials, ratio test is typically one of the things you use quite a bit. Okay, now we're going to go to a new test. We're going to look at the root test. And one of the things that you want to kind of get down as you do these is, when is it a good situation to use the root test? Well, usually what happens is what you look for is something like this, something to the k power, okay? Or maybe something even to the k plus 1 or k minus 1 or something like that. So typically that's what you do. So what we do is we formulate this, and then we use, the textbook uses the Greek letter rho, okay, to represent this root. So what we do is the k root of the sequence, okay, and then the convergence turns out to be the same way as it did on the ratio test. If your limit is between 0 and 1, including 1, it converges. If it's bigger than 1, it diverges. If it's equal to 1, it's inconclusive, okay? So what you want to see on this when we get into testing, I tell you what test to use. That helps you a little bit. Now, you want to get to a point where you kind of see which case applies to which, but this has a k power on it. So this is a good situation to use the root test on. You could use the ratio test too on this too, and I'm sure it would work just beautifully. So let's start by doing this. We say rho, and then we're going to do the limit as k goes to infinity. And then what we do according to the root test is we just do the k root of whatever that expression for the sequence is. So that would be 2k over k plus 1 to the k power like that, okay? And then that's how that's going to work out. So this is a beautiful example of the root test, okay? All right, so we have the limit as k goes to infinity. Now tell me what's going to happen to this thing right here. Radical comes off, right? See, it's no different than having something like this. Like if you had the third root of x to the third, that's x, correct? So the radical comes off, okay? So these things divide like that. So what you'd end up having then is you would just have 2k over k plus 1 like that. Okay, so that's what you'd end up having. Now all you got to do is do that limit, and if you do that limit, you could work that out. Now I think so, I have an extra 2 in there, don't I? Okay, oops. Okay, so what's the value of that limit?
2.
How do you know it's 2, by the way?
Because k.
Okay, it's got you can think of the degree of the top and degree of the bottom are the same. So one way you can think of this, there's 2 ways, or more than one way you can do this, is since the degree of the top and bottom are both 1, There's your answer right there. That's like a horizontal asymptote, so that's just equal to 2. You could also do L'Hopital's rule. If you did L'Hopital's rule, you would just do the limit. K goes to infinity. If you do the derivative of the top, you get 2. The derivative of the bottom is 1, so you get 2. So don't forget about L'Hopital's rule. It comes in handy. So anyway, what we have is we have that that's equal to 2. So where does that fall in the root test? What would be the result? You're greater than 1, so what do we conclude? It diverges. So what we would say is, therefore, this diverges by the root test. You can just write it that way if you want to. The series diverges by the root test. Okay? All right, so that's how you do that. That's a real simple example. All right, any questions about that? Okay? All right, let's do something else with the root test here on this next page. Okay, now sometimes your series can be written, not in an explicit formula, that it can be written this way. So if it's written this way, you got to develop that explicit formula for them. Okay, so we're going to look at one of the things that you have to do, and I failed to mention this. So if you got a root test, you need to have non-negative terms. Okay, so or positive terms. So you've always got to have. You can have 0. That's the reason they say non-negative instead of positive terms. So you can actually have 0 or some positive number. So does this have all non-negative terms? Yeah, pretty clearly it does. Okay, so you've got that condition done. Okay, now what we want to do on this is we want to see if we could write an explicit formula for this. So there's a couple of ways you could do this. You could let K either be the denominator, or you could let it be this numerator. What I'm going to do is I'm going to let K start at 2 and then be these numbers right here. That's what I'm going to do. It'll probably work either way, but what I'm going to go ahead and do on this is just do this like this. So if I was to go through and do this, I'm going to put my K here and my K there. So what would be this thing right here then? How does 1 relate to 2? Yeah, that'd be K minus 1, right? So you would end up having that right there. So just kind of convince yourself that that works. Okay, so like for instance, if K is 3, well then what would you have? You'd have 3 there, you'd have 3 there, you'd have 3 minus 1, you'd have 2/3 of the third. So that's your explicit formula. Now you probably could also let K be the 1, 2, and 3, and then this would be K plus 1. And it would work fine. I think either way you do this, this is just what I'm going to choose to do. Okay? All right, so what we're going to do is let's write this as the series. And we're going to do K minus 1 over K to the K power. And then this series is going to be going from K equals 2 to infinity like that. You can start the series at 2 if you want to. Generally, we start at 0 or 1. So I'm just going to write it that way. Okay, so one thing, if you look at this particular problem, it's kind of hard to tell if this series is going to converge or diverge. Now, one thing that I notice on this thing right here is going to get closer to 1. If you go way, way out in this series, like if you went to the 100th term, you would have 100th power, you'd have 99, right? Isn't this thing right here getting close to 1? That's my point. And 1 to any power is 1, right? So it looks like as the series goes out, it looks like it's going to 1. You see what I'm talking about? Now see, we're going to do the limit of the series, so sometimes you can tell that by writing the terms out and seeing what happens. Now we want to apply this using the root test, so what we're going to do, and part of the reason I did what I did is I wanted that to be a K power. Okay? I could have done this as K, I could have made it K over K plus 1 to the K plus 1 power, but it's a little easier to use the root test if it's just something to the K power. So that's why I did that. Okay? All right, so what we're going to do is we're going to formulate this row as what we use for the root test. So we're going to do the limit as K goes to infinity, and then again what we're going to do is we're going to do the K root of K minus 1 over K like that. Okay, well, let's see, that whole thing is to the k power. All right, so what happens to the radical again? Goes away. That's what the benefit of the root test is it makes that that radical go away and that power go away. So you would have the limit as k goes to infinity, and then you would end up having the expression k minus 1 over k like that. Okay, what's the value of that limit? In your head, boom, boom, like in 2 seconds. 1, okay, right? Okay, that's because the ratio of, you'd have like a horizontal asymptote at 1. If you did L'Hopital's rule, this is what you would get. You would get limit k goes to infinity of 1 over 1, so it would be 1. Okay, so what do we get? Okay, p is equal to 1, what do you get? Test is inconclusive. Okay, so anytime you're doing these tests, go back to that theorem, and that'll tell you what the results are. So what you would say is, therefore, the series, you just say, therefore, it's inconclusive by the root test. Always state what test that you're using. Okay, that's the way I want you to do that on a exam. Okay. All right, so those are a couple of examples of the root test. Again, when do you use a root test? What are you looking for? Something to the k power, or k plus 1, something like that. Typically the k power. That's what would tell you that that is the most applicable test in that situation. Okay. Now, one other thing that we could do on this then is we could, now if it's inconclusive, you can go try another test. One thing I'm going to do is I'm going to go ahead and do the divergence test on this. And then when we do the divergence test, remember what you're doing is you're just doing the limit as k goes to infinity of, you're not doing a ratio or anything, you're just doing this expression right here. So let's see if we can figure that out. And what you're doing on the divergence test is, if that limit's not equal to 0, then it diverges. So we usually use the divergence test to tell if something diverges. Okay. Now this one could be done like this. You could break this up as this part inside. You could split that fraction apart, and k over k would be 1, and you'd have 1 over k to the k power. Okay, so that's a real beneficial way to break that up. Now, what's going to happen if k goes to infinity? What you're going to have is you're going to have 1 plus 0 to the infinity power, so that's going to be 1 to the infinity, so that's 1, right? Okay, so that would mean, is since it's not equal to 0, then we could conclude that this diverges by the divergence test. Okay, so a lot of times the divergence test is the simplest, quickest way to tell if something diverges. Okay, so if you can do the limit of whatever that sequence is, that explicit formula, if it's not equal to 0, problem done, we know it diverges. So even though the root test was inconclusive, the divergence test is conclusive. Does that make sense? Okay, so this one right here, the way that I look at this is, it's inconclusive because the value by the root test was 1, so that's inconclusive, but divergence test was not equal to 0, so that means it diverges. So I went ahead and did that. Yes?
I know the answer's still the same, but how did that turn positive and that's a negative?
Are you looking at when I did the divergence test?
Yeah.
Okay, so which part are you looking right there? Oh, that doesn't become, yeah, I've been doing that several times today, haven't I? Actually, I'm lucky because I still get the same result. Yeah, that should be minus 1 over k. Sorry about that. So you still get 1, don't you? Yeah, okay. But yeah, you're right. Okay, any other questions about that? Yep.
If you happen to ask us a similar question on the test, can we just start out all series with the divergence test to see whether or not it diverges without using?
Yeah, you can always do that, but generally the way I test is like I said, I tell you what test to use. So like on a problem like this, I'd probably say test by the root test. And the reason I have been doing that for a while is because if I didn't do it that way, students could use the ratio test pretty much on every problem.
Yeah, okay.
So I mean, it's like, so we're kind of learning the different tests. So that's the simplest way to test is to tell you which test to get, that you're going to do. Okay. Okay, so let's see. Let's now look at the comparison test. So the comparison test, we have two types. We have what we call the comparison test and the limit comparison test. Okay, so what you kind of do on this is you try to compare the series that you're working on to a series that you know something about. Okay, so for instance, if you go back, and I can't remember, I think the first page of either this handout or the 8.4 had a bunch of things we knew, like harmonic series, P series, geometric series. Some of those things you know, like for instance, you know this one, which series is 1 over K? Have you got that down yet? That's the harmonic series, and that one diverges. Okay, that's harmonic. So you might be able to take a series that you're working with and compare it to a series you already know. Another one, good example would be this one, 1 over K to the P. That's a P series, right? So what you know on a P series is if P is greater than 1, then it converges. So what you're going to do, the comparison test tends to be very useful if the series you're analyzing can compare something to something you know. So let's take a look at this series I'm looking at. Let's just pretend like the 4 is not there. What is that? That's a P series. Does that converge or diverge? Converges because that exponent is bigger than 1. So what we're going to do when you do a comparison test, the convergence establishes on this. So you're going to, B sub K is what you're comparing it to. So if you find the series that you're working with is less than the series you know, then they're both going to have the same answer. So for instance, if that converges, so does that. Okay, for divergence it goes like this, it's just backwards. If A sub K, the series you're working with, is larger than 0 and larger than all of the terms of the series you're comparing it to, then it diverges. Okay, so that's how you do that. So what you're doing with this is trying to find some sort of a series that you know something about. Okay, so what did we say? This one, the similar series on this one would be 1 over K to the second. That's a P series. And since the exponent 2 is greater than 1, we know it converges. So that means since we know that this converges, what we're going to say is B sub K is equal to the series 1 over K to the second. K goes 1 to infinity. Okay, and we know that converges, so that means we need to see if this inequality right here holds. That's the idea. Okay, so what we're going to end up doing on this is we just end up kind of formulating this right here. So we know that we've got a convergent series right here, B sub K. So let's write down this inequality. We have 0 less than A sub K less than or equal to B sub K. So what we're trying to do is establish if that's true or not. Okay? So if you're comparing it to a convergent series, really all you got to do is two things. You got to make sure that your series has all positive terms in order to use the comparison test. Then you got to verify this inequality. Okay, that's it. Okay? Now this has all positive terms. Can everybody do that in their head? Okay, there's no negative anywhere to be found. K is always a positive number, so it's got positive terms. So let's write down what we have. Well, A sub K is what I gave you. That's 1 over K squared plus 4. And let's see if that's less than or equal to 1 over K squared. Now, this kind of thing right here, most of the time, you just do this in your head. Okay? So what happens on this is, just think about this. Let's say, for instance, that K is equal to 1. Well, then you would have 0 is less than 1 over 1 squared plus 4, less than or equal to 1 over 1 squared. Is that true?
Yep.
Absolutely. Because what you get is 0 is less than 1/5 is less than or equal to 1 over 1. The idea is, if the denominator is bigger, then that's going to be a smaller number. Now, this is a basic thing you do on the comparison test all the time, so you want to make sure that you have this down. Like if you had 1 over 10, is that smaller than 1 over 10, 1 over 2? Of course. How come? Because that is smaller, it is bigger than that. That's the way that works out. So the bigger the denominator, the smaller the fraction, right? Okay, so what you'd have is this is true, and you just reason that out in your head. There isn't really anything to show. You can do this if you want to. You can cross multiply But if you cross multiply, you got to do it this way because you'll get everything wrong. You could say 1 times k squared is k squared. Then if you go this way, you would get k squared plus 4. Now that's obviously true, isn't it? You add 4 to the same number, it's going to be bigger, okay, every single time. So that would do it then. So what we would say is, therefore, we would say that the series converges by the comparison test. So when you're doing a comparison test, you want to use that when you see the series I gave you can easily be compared to some series you know the convergence or divergence of. Okay, does that make any sense? Okay, so sometimes it works well, sometimes it doesn't. Okay, this is just a good example. This is very close to a p-series. That's the idea. Okay, and what you're trying to find on this is that, again, this inequality is satisfied by that. Okay, the one that you're looking for is less than the one you know. What you're doing is you're establishing a bound on this. So this is bounded by a series that has larger terms that we know converges. Does that make any sense? The idea is kind of like this. If you had a series like of partial sums that was, and these dots are representing the sum converging to some value. Well, if you had, like, if that's b sub k, if a sub k is always less than it, and it's always bigger than 0, it's kind of almost like a squeezing theorem in a way. It's bounded by 0 and another series that you know the convergence of. Does that make any sense? Okay? These tests are not that bad to do, but you just have to follow what they tell you to do. So if you're doing your homework and stuff, just look at the theorem and do exactly what it tells you to do. Okay? Mostly it's what you're going to be working with some algebra and stuff. Okay, let's do a couple more things with a comparison test here. Okay? And show you kind of what happens. So let's look at this one. Now, if you're doing a comparison test, and I'm asking like on a test for comparison test, I'm going to give you some sort of a series that easily compares to something you know. So the way I'm going to start this one is by just pulling out the constant. So you can always do that. So we have that times the series k equals 1 to infinity, 1 over k plus 4. Okay. Now, if you ignore the 4, tell me what you see. What is 1 over k? Which series is that? Which one? Begins with H. Second letter's A.
You said harmonic.
I'm sorry, I'm not hearing good today.
Oh, harmonic.
Harmonic series. Okay, very good. Okay, very good. What do you know about the harmonic series? That one diverges. Okay, so the similar series, and we always let that similar series be b sub k. So let's let b sub k equal the harmonic series, which is 1 over k. Okay, and again, we know the harmonic series diverges, so that means really what we got to do is we got to see that this inequality right here holds. Okay, we need to do that. So we need to see that a sub k is bigger, all the terms are bigger than b sub k. Now, you guys got to make sense of this, because that's the only way you remember this stuff is to make sense of it. This is how I make sense of it, okay? If you already have something that diverges, tell me if it makes sense that this one would also diverge if this inequality held. If every term is bigger than all the terms in the divergent sequence or series, wouldn't it have to diverge also? It would kind of be like this. You have 0, you have a series b sub k that diverges. Well, so would a sub k if that inequality held. It would have to. Okay, it's kind of like not the squeezing theorem. Okay. All right, so what we're going to do on this then is we're going to see if this inequality holds then. All right, so just kind of disregarding the point 0, 0, 1, we need to look at this. So we're going to write down 0 less than b sub k, that's what we're comparing it to, less than or equal to a sub k. That's what we need to see if it holds. If it holds, it diverges. If it doesn't, we can't conclude anything from this test. So let's see what we have. We have 0 less than 1 over k, less than or equal to, and then don't worry about the 0.01 because that's a constant anyway. Okay, if that diverges, multiplying it by 0.001 isn't going to make any difference. So let's put that like that then. Okay, Now, let's see. Is this inequality right here true or false? Careful. It's false, okay? The reason is, and again, if you cross multiplied, and if you cross multiply, you can go this way. You've got to go that way first. So if you did that, you would have k plus 1, k plus 4, less than or equal to k. That's false, okay? The other way to look at this is like just pick something for k. If k is 10, you have 1 over 10 less than or equal to 1 over 14. That's clearly false. Everybody agree? Okay, so that means that this would be inconclusive. Okay, so by the comparison test, what we really do is we get something that's inconclusive. Okay, now with this one you might be able to do the divergence test on, possibly, but I think it would end up being inconclusive too. There's going to be another way that we're going to do this a little bit later in the section. I think I'm going to show you a different way to do this. For now, it's inconclusive. The comparison test doesn't work, doesn't do anything for us on that problem. Okay, does that make sense? Okay, so remember what you're doing is you're finding B sub k is something you know something about, and then see if the inequality holds. If it's divergent, in this case we're comparing it to a harmonic series. That's why we looked at that particular inequality. Yes?
So having it inconclusive is okay? You don't have to do another test?
No. I mean, if my directions are examine the convergence by the comparison test, your answer is inconclusive. Okay? Now, what you would do on this one is, this is better suited for what we call the limit comparison test. This is a different type of test that would work well on this one. Okay, let's do this one more example of a comparison test then, okay? All right, so let's see. What do you guys think would be a good series that you know something about that you could compare this explicit formula in that series to?
P-series?
P-series, exactly. Which P-series? 1 over k squared, because I see 1 over k squared. You see it too, right? It's embedded right there. There's 1 over k squared. So what we're going to do is we're going to compare it to 1 over k squared. Okay, that is a P-series. Does this P-series converge or diverge? How come? Okay, P is bigger than 1. See that number right there? That's what P is. 2 is greater than 1. So what that means is we need to now, when we look at the divergence test, since we're comparing it to a convergent series, we need to see that this inequality right here holds. Okay, so let's write that in general inequality down. So that's 0 less than a sub k. That's the series I gave you. And let's see if that's less than or equal to the P series B sub k like that. Okay? All right, so this is a sign in the numerator. That makes that fairly easy. Think of this kind of like the squeezing theorem. So this is going to be sine of 1 over k all over k squared, and then less than or equal to the P series 1 over k squared like that. Okay? So let's think about whether this would be true or not. Now you got to kind of look at this. You can do this in your head, but what do you know about, see, notice that the denominators are the same, right? What do you know about the graph of a sine of anything? Okay, what's the amplitude? 1. So what would be the maximum value on this sine? If you did the max of the sine of 1 over k, what would you get?
1.
You get 1. So it has a max of 1. All right, so this thing right here is always going to be less than like that. Now, if you do the sign over here, the other thing that you kind of get into with this is that thing is always going to be less than 1. Since the sine of 1 over k is going to be less than or equal to 1, then that part of the inequality holds, doesn't it? Everybody agree with me on that? Okay, that's for that reason. Now, if you looked at the sine of 1 over k, well, k is always a positive number, and this would always be in radians. One thing you got to kind of think about like this, if you did a reciprocal of k radians, okay, you would always be in a certain quadrant on this one if you think about that. Okay, like you would have numbers like 1 over 1, 1 over 2, 1 over 3. Aren't those always quadrant 1 values? They are, because quadrant 1 is always between 0 and pi over 2, and pi over 2 is like about 1.5. That's about 3 over 2. So you're always in quadrant 1, and if you're always in quadrant 1, what is the value of the sign? Positive, okay? So for that reason, since that's always positive, then that means that it's going to be greater than 0, okay? So what you end up getting is, you know for a fact that 0 is less than sine of 1 over k is less than or equal to 1. You know that for a fact. You know the sign will never get bigger than 1 because the amplitude's 1, but it's also bigger than 0 because you're in quadrant 1. Does that make any sense? 1 over k is always a quadrant 1 angle. You're always between 0 and 1.5. So that's how that goes. Okay, so that would be true. So that inequality is true. So then what we'd do is we'd say, therefore, the series, since we're comparing it to a convergent series, p-series, we would say that the series converges by the comparison test. Okay, problem done. We don't know what the value is of that series, but we do know it converges. That's the idea. Okay, does that make sense? You do have to make sure that that sign is less than 1 and bigger than 0. That's trig knowledge stuff, is what that is. Knowledge of graphs. You have to be able to reason that out based on what you know about the sine function. And it is bigger than 0, but it is less than or equal to 1. Okay, next thing I want to go to is the limit comparison test. And on this next page, what I want to look at a little bit here, the limit comparison test, what we tend to use it for, you might want to write a note for what you're looking for. You usually look at rational functions where you have powers, like maybe you have something like, kind of like this problem here. You might have like k to the third plus a bunch of stuff, and then you might have k to the 7th plus a bunch of stuff. That's what it's typically used for, because then you can usually compare it. Usually what you're going to use is compare it to the harmonic series, 1 over k, or compare it to a p-series, where you have 1 over k to the p power. So what you're looking for, and this is why you use a rational function on it, if you just block off all those terms right there, isn't that just 1 over k squared? So that kind of looks like a p-series, doesn't it? Okay? If that was k to the third and k to the fourth, then it might be, you may end up doing something more with the harmonic series because they're 1 off. But what you do on this is you formulate a ratio of what you're given. A sub k is what you're given. B sub k is what you're comparing it to. So one of the key things that you're doing on limit comparison is you got to think about how far those highest exponents are off. So first of all, this one is going to have all positive terms because you do have to have that. And you can verify that by writing out the terms if you want to. And the denominator is always going to be bigger than 1. Let's see, yeah, that'll always be bigger than 1, so would the denominator. Okay, so what we're going to do is we're going to compare this to the p-series. So what we're going to do is a sub k is going to be what I give you. Okay, so that's what you're given. That's what we're analyzing. Okay, now b sub k is, if you look at this, you have k squared over k to the fourth. That's 1 over k squared, right? Okay? You can't just compare it to any p-series. You want to compare it to that one, and you'll see how this works out once I do that. So we're going to let b sub k equal 1 over k to the second. This is usually a good situation where you use the limit comparison test. Okay? So what we do is we formulate this ratio right here. Okay? So we're just going to let that value just kind of, let's work out the limit k goes to infinity, and let's compare a sub k, which is what you're given, so you just write that down. Okay, then you're going to divide it by what you're comparing it to. So we're comparing it to b sub k, so we're dividing it by 1 over k squared. Okay, and you're going to do the reciprocal of that anyway, right? Okay, so it's kind of like the ratio test in some way. You're comparing, you know, it's the ratio test, what you were doing was comparing the next term in the sequence to the previous term. What you're doing on the limit comparison test is you're forming a ratio of what you're given to what you're comparing it to. So what I'm going to do is I'm just going to change that to times k squared over 1 like that. Okay? Now, you know why I'm doing this? Because when you multiply that out, k to the second times k to the second is going to be k to the fourth. That's why I'm doing that. So what we're going to do is we're going to go ahead and multiply everything out on this. So we're just going to do limit k goes to infinity, multiply out the numerator. You're going to just distribute, so you're going to have k to the fourth plus k to the third. So we're going to have, k to the third minus k squared in the numerator. Then the denominator is going to be k to the fourth plus 4k squared minus 3 like that. Okay, so do you know what the value of this limit is? You need to. If you don't, it's 1. How come? Yeah, right there. Remember, the degree of the top and bottom are the same, so the horizontal asymptote occurs at the ratio of those leading coefficients. So that's 1 over 1, okay? So if you look at the directions to the limit comparison test then, is we call this value L. So L is equal to 1. So here's what happens. There's 3 situations. If you get a finite value, then it's going to say that these things, that the series you're comparing it to, they either both converge or both diverge. Okay? So one thing we know is the P series converges, right? And since this is finite, since you would end up having 0 less than 1 less than infinity, then you can conclude that this series is going to converge. Okay, so you've got that. You've got a convergent series, and you've got a finite answer. That means that therefore you can draw your conclusion. So we'll say therefore the series that we're working on is going to converge. And I'll just abbreviate this by the limit comparison test. Okay, so again, whenever you're doing these tests, look at the theorem. The theorem tells you what to do. Okay, so as you're doing homework and stuff, just refer to this over and over again. So we got that, and we compared it to something that already converged, therefore we converge. Okay, does that make sense? Okay, yes.
Can you tell me just real quick why again you go to L equals 1, but then due to the comparison test in the box that you were able to find that it converges because you were like 0,
okay.
1, yeah.
Okay, because what you're doing is you're looking at this inequality. So L has to be between 0 and infinity. In other words, the value of this limit just has to be a finite number.
But then on the bottom it says if L equals 0 and the series converges, then A converges, but you put down there that it equals 1.
Well, there's 3 situations.
Oh,
if the value of the limit is anything other than 0 or infinity,
yeah.
Okay, it's going to be, if it's some positive number, a finite positive number, then both the series you're comparing to and the one you're finding are going to both converge or diverge. Okay, that's what that says. If the value of that limit was 0, then they're both going to, then if b of k converges, then that will too.
Okay.
If they're infinity, then they're both going to diverge. So there's like 3 situations.
It just, if it happens to come up with 0 or infinity, then those are...
Right. You could even say by case 1 on this if you wanted to. That's right. Okay. So it's got to be one of those cases. All right. Okay. Does that make sense? Any questions? Okay.
So we're going to have to memorize this theorem.
You do. Okay. That's why I said start making you some little flashcards out and knowing what they are. It seems real intimidating to students. But aren't you seeing that 0 and 1 showing up over and over and over again? There's slight little twists to a lot of these, but not all of them are going to be that way. So let's go to number 22. And what we're going to do now is we're just going to let's look at the test. Okay, so like I say, when I test, I tell you the test to use. That's the best way to keep you from doing the ratio test on every single problem. Okay, so this one right here, if one of the things we said with this one is if you had a power there, like a K power, then a lot of times a root test was good. So like if you look at number 24, that one looks a whole lot like it could be a root test possibly. And then this one right here is also maybe a root test. Okay, the reason? Because you have a power of K. Even K squared might work out okay. So let's go ahead and do 22 by the root test. When you're doing the root test, what you're going to do is we usually use row. I don't care that you do that. I mean, it's just that's what the variable is our textbook does. So what we're going to do is we're going to do the limit as K goes to infinity. Then we're going to do the K root of this expression right here then. Okay? So we'll kind of see what we have here. Now, one thing that's kind of helpful on this is, let's say, for instance, you had something like this before I do this. Let's say you had some expression and you had like a third root. Now, let's say you had something like this. You had K, let's say we had like K squared and you had a fourth root. Just say that you had something like that. Well, how do you write that without a radical? How do you write this without a radical? K to what power? 2 over 4, right? Okay, so you want to know that. So in general, if you have like K to the n power with an n root, you write that as K to the n over n. Okay, you got to remember that when you're doing this problem then. So that's what we're going to do. So I'm going to just write the next step kind of like that and see where that takes us then. Okay, so that's going to be written as 1 plus 3 over K to the K squared over K. Okay, like that. All right, so we can do that. And of course, that thing right there is going to simplify to what? To K, right? Okay, so we can do that. Okay, so let's see what we have. So now what we have is rho is equal to the limit, K goes to infinity, of 1 plus 3 over K to the K power like this. Okay, now what's going to happen with this one, I'm going to look at specifically something like this. There's something I want you guys to write down too, because this shows up from time to time. And you probably need to make a note of this then, so because you might not always see this. So we got the limit, if you do the limit of K goes to infinity of 1 plus 1 over K to the K power, that's equal to E. We've actually looked at that before, but that's one way to define what the exponential E is. It's this particular limit right there. And if you look at this problem, it looks like almost the same, doesn't it? Okay, so I have a suspicion it's going to have the value of this limit is going to have something to do with E. Now what I'm going to do is a real simple substitution. Because I want to turn this into this, I'm just going to pick a variable and say something like, let's say M or whatever. So I'm going to let M be 3 over K. Okay, if you solve this particular thing, so I'm going to call that M, and if I cross multiply this, I would get K times M equals 3. I want to solve for K to see how I change this thing. So if I do that, that would be, let's see, if I divide both sides by M, I would get K equals 3 over M like that. Okay? So what I'm going to have on this then is, let's see, I'm going to, hold on. Yeah, that looks good. So what I'm going to do is go ahead and change this to the limit. K goes to infinity. Now let's see, that's not what I intended to do. I want to change this to 1 over K. This is what I want to do, sorry. Want to do this. Okay, I want this thing right here to become this. So what I'm going to do is let 3 over K be 1 over something like 1 over M. Because I'm wanting it to look like this. Okay, just to give you the, I want to just show you how you could get the specific value of that. So 3 over k is going to get changed to 1 over m, like that. Okay, that's why I want it to look like that. You guys see what I'm trying to do? Okay, now you can cross multiply this. If you cross multiply this, you would have 3m is equal to k. Then you want to know what k is, so that k is going to now be 3m, like that. Okay, so now if you change this, you're going to have 1 over 1 plus the 3 over k, what's that going to become? 1 over m, which we want. And then the k, what's that going to become? 3 to the m. See, what I'm trying to do is I'm trying to make it look like this thing. And what I can do is I can write this like this now. I can write this as the limit k goes to infinity of 1 plus 1 over m to the m power, and then the whole thing to the third. And that's a basic property of limits you can do. Okay? One of the limit properties that you've learned before is you have a limit of something to a power. You can do that whole power outside the limit. Okay? So here's what you end up having. Okay? So tell me what that is. What's the value of that? That's e. Okay, so what do you have? E to the third. Okay, all right. That's how that 3 changed that, as it made it to the third power. Okay? You could probably reason out that this particular limit, you couldn't figure out that it reaches e to the third without going through this, but you could probably reason out that it goes to a finite value in your head if you thought about it. Okay, so anyway, what are we doing with this one? If we're doing a root test, what we want to do is we want to see what the value is. Okay? That doesn't hold. E to the third is clearly bigger than 1, right? So what do we have? Okay, it's bigger than 1. So what's it going to do? Okay, it's going to diverge. Okay? Okay, so we would say, therefore, the series diverges by the root test. And that's because this is bigger than 1. So this is like case 2. And write that down if you want to. You don't have to state it that way, but it's kind of good when you're writing your notes to know which case that went along with. Okay? So I would say that it's probably a pretty good thing to know that, because that does pop up every now and then. Okay? Okay, so that would be a root test on that. Okay, let's do this one, and then let's do 30. And let's see, I think that's probably, I think this number 30 I bypassed. This is earlier in your notes, but I want to show you the correct way to do that now. Okay, so number 24, why would a root test be a good way to do 24? What do you see? It's to the k power. Okay, like the last problem was to the k squared power. Those are kind of good indicators. So what we're going to do is let rho be the k root of what we're analyzing. So we're analyzing 1 over ln k plus 1 all to the k power, like that, and then it's the limit. So I'm getting lazy about my limit there. Okay, so we're doing the limit. K goes to infinity. And as we're doing these different tests, we're kind of working with the limit over and over again, aren't we? Okay, so they have a lot of commonalities in those. Okay, so what we're going to have is limit k goes to infinity of, this is going to now be 1 over ln of k plus 1, like that. Okay? All right, now, what do you think the value of this limit is? Okay, what kind of number, what's happening to the denominator as k gets bigger? You're really getting the ln of an infinitely big number, agree? What's the ln of infinity? That gets bigger and bigger and bigger without bound. Remember, the ln graph does something kind of like that. It just increases forever. So you're going to have 1 over infinity, so where's that going? That goes to 0, right? So now if you look at your results on the root test, as you're learning this, well, okay, if it's equal to 0, then which case holds? That case holds, right? So what's the answer? Converges. Okay, the value of rho was equal to 0, so that inequality would hold. So we would say this one converges by the root test. That's really case 1. Okay, it's basically that 0 less than or equal to rho less than 1. Okay, rho was 0. That's how we know that. Okay, that was real simple. Sometimes the root test is a very simple thing to apply. Okay, any questions? Okay, I'm kind of now to the point I'm just sort of summarizing all the tests we've learned. Okay, now this one we're going to do, I'm going to show you how to do this one with the limit comparison test. And if you're doing a limit comparison test, what you want to pay attention to is B of k. Tell me what B of k means in the limit comparison test. That it's a series, right? That you know what about. That it converges or diverges. You're comparing it to something you know something about. That's what you're doing on the direct comparison test or the limit comparison test. So what I'm going to do on this one is I'm going to start by doing this, just bringing that 0.01 out. So I've got 0.001, then I've got series k equals 1 to infinity of 1 over k plus 4. Okay, now what I said that we do on the limit comparison test is a lot of times rational functions. That's pretty important to pay attention to, rational functions. What do I mean by rational function? Just a fraction with powers of k. If you back up, I did this problem right here. That's a rational function. And the exponents were off by 2, so we divided by the power series so we'd end up getting that limit. See, what happened is we ended up using 2 because that numerator was 2 less than the degree of the bottom. That's kind of the thought process you go through on this limit comparison test. Okay, so what we're going to do on this is, see, kind of like that problem we did before when we had k to the second over k to the fourth, ultimately we divided by that power series. How come? So that we would end up with k to the fourth over k to the fourth.
So you're going to multiply by k?
There you go, good. That's what I'm getting to. Okay, so basically you could think of this as k to the 0 over k to the first plus 4. So you're going to compare this to 1 over k. All right, so what we're going to do with this one is let's go ahead and let's let b sub k equal to 1 over k. All right, what kind of series is that? Harmonic, good. You're getting faster. What do we know about the harmonic series? It diverges. Okay, so we're going to compare this to something that diverges. Okay, so what are you going to do, okay, on this one? So this one isn't going to, case 2 has nothing to do with this problem. Okay, it's either going to be case 1 or case 2. So if we do our limit of this ratio, if L turns out to be finite, then that means that since B of k diverges, so will A of k. Or if L turns out to be infinity, then they're both going to diverge. That's how that works out. So when we put this together, we're going to do this then. We're going to just bring down the 0.001. Okay, then we're going to do the series k equals 1 to infinity. And what we're going to do is compare the series we have, 1 over k plus 4, and we're going to divide it by b sub k, which is the harmonic series. Okay, I'm just writing it that way because what are you going to do anyway? You're going to multiply by the reciprocal. Just learn to save that step and do that. Okay, is everybody with me so far? Okay, see, just like that problem we did earlier, the exponents are going to match now, aren't they? And that's the whole key. So what you get, and I forgot to do my limit, so I'm really doing a limit on this. So what I'm doing really is, need to have a limit in there. So I've got 0 point, and you don't even have to worry about the 0.001. What you're going to worry about is just the limit, k goes to infinity, of k over k plus 4. So what is that? That's 1. Okay, is that finite? Absolutely. So this is case 1. Okay, so since that turned out to be finite, okay, case 1 would be what we're looking at then. So that is between 0 and infinity. So you basically got 0 less than 1 less than infinity, the value of that limit. That means they both converge or they both diverge. So what do we know about the harmonic series? It diverges. So what do we conclude about our series? Diverges also. Okay, that's the way that goes. So the series diverges by the limit comparison test. Okay, all right? So seriously, when you do this, and when you get in higher math, I mean, this is what you do as a student. If you don't know how to do something, you look at the theorem. And the theorem tells you how to do it, right? It tells you exactly what to do on every one of these problems. Okay? This stuff is real abstract, and you're not at a level in math where you can really prove how the limit comparison test and ratio test works. Prove that it's in fact a theorem. All you can do is kind of learn how to use this stuff. You will see this, if you're going to go to diff-EQ, you will see series a little bit more in diff-EQ. I don't think you see it much in Calc 3. You might a little bit, but I think in diff-EQ you start seeing it again. And I'll tell you something that I thought was kind of interesting. I know a professor over at CU Denver who's a chemistry teacher, and like I was looking at one of his tests he gives to a senior level chemistry class for chemical engineers, and he has all these calculus formulas, and some of them are series formulas on there and stuff. So it does show up quite a bit in different areas. I don't know enough about chemistry to know where this stuff shows up, but he was showing me the formula sheet he gave a test, and it was all Calc 2 stuff on it over and over again. I should show that and bring that to class. So it had series and integral formulas and all kinds of stuff. Okay, so that will